All right, y'all, we don't have the best lighting right now, but I'm just recording the um, correlation and regression lecture for you guys. So let's dive in. I'm going to share my whole desktop. All right, so correlation and linear regression have to do with what's called a linear relationship. And that's essentially when the relationship between two variables can be most accurately represented by a straight line. And so correlation is just when you have two sets of data in time and you're just looking at whether or not they're related. And linear regression, as we'll get to in a little bit, is more about whether you can predict one from the other. So correlation is a statistical technique that is used to measure and describe the direction and magnitude of the linear relationship between two variables. The two variables are typically observed as they exist in nature, so you're not manipulating anything. And it requires that you have two scores for the same person. Otherwise, you can't have a relationship between the variables. And so it's the measure of the relationship between variable X and variable Y. So the things that we talk about for this relationship, we talk about the characteristics of the relationship, and there's the direction of the relationship. So if it's positive, that means that both variables change in the same direction, such that if there's like it says, if higher temperature equals higher ice cream sales, whereas when you have a negative correlation, that means they go in opposite directions. So higher TV viewing equals, relates to a lower GPA. And then the second thing you can measure is the degree of the relationship. And that's kind of talked about as the magnitude or the strength. And it can vary from there being no correlation between the two variables, that they're not related, to that there's almost a direct relationship of 1-to-1 between them, right? So from no correlation to very strong. So this is kind of what some different plots look like of correlations and whether or not they're strong. So as you can see here, you have a strong positive correlation because it's almost a 1-to-1 relationship between the variables. This is a weaker positive correlation. As you can see, there's less of a true pattern there. And then this is obviously this is just as strong of a correlation, but it's negative because higher values over here equal lower values over here. As you can see, this line, it's not as well defined. So that's what we would call weak negative correlation. Moderate correlation, you can see that the dots are still in kind of a line shape, but not as closely in a line as they are for the strong. And then when you have no correlation, there's just no pattern at all to the variables. So that's why you'd see no correlation here. So correlations are measured using the Pearson correlation. It measures the degree and direction of the linear relationship between two variables. And it can range from -1 to +1. And the sign tells us whether or not the relationship is positive or negative, and the number tells us the magnitude. And the higher the number in either direction is the greater the strength of the correlation. So we look at some of these plots. As you can see, this is a perfect relationship where 1x would equal 2y, or 1x would equal 1y, 2x would equal 2y, and as you can see, it's a relationship of r equals +1. And the opposite down here is r equals -1. So then you see a slightly weaker relationship, but still pretty strong, as r equals 0.91. And then one where it's really not as strong and not as closely together. You see that you have only about r equals 0.5. And then here you see you just have no correlation at all. There's no relation between your variables whatsoever. So you see that you have r equals 0. And again, you have a negative correlation that's moderately strong, so it's that 0.66, and then you have a really strong one that's a -1. So let's go ahead and just run this. I'm going to go ahead and exit out of that and open up this birth weight data set, which will be on D2L. All right, that's opening right now. I'm going to try and keep this video shorter just because you guys can go back and rewatch it when you want to. I don't want you guys to have to watch a super long video. All right, the data set's still loading. So we want to know if there's any relationship between birth weight and IQ later in childhood. So from basically what we're wanting to do is, let's see. Get back my slides over. Because the data cycle is being rendered, I'm going to reopen it. But essentially, what you want to do here is and 3. I really don't have to record this. Hopefully this. There we go. Close up soon. Let me stop sharing the screen for a second while it figures out what it's doing. Okay, it's back. You guys are just going to get to deal with that lovely delay because I'm not going to reshoot that. Okay, I'm sharing the desktop again. Let me go back in here. It's opening both of the data sets. I guess this is a good time for the question. What food did I just eat tonight? And the food that I just ate for this video was I had a bowl of ice cream. So that'll be your answer for the question. What food did Michael eat? The answer is a bowl of ice cream. All right, our data is open, so I'm going to go back to the PowerPoint. So I'm going to do graphs, legacy dialogues, scatter, dot. And this is going to help us look at the relationship on a scatter plot before we actually run the calculation. So like I said, graphs, legacy, scatter, dot. Okay. Let's see, graphs, legacy, scatter, dot. I believe we want to pick simple scatter. And just put one variable on the y-axis and one variable on the x-axis. And then the last thing we want to do is we're ready to go. So now we're going to have a graph to look at in our output. And does it look like we have anything going on? I think it kind of does. As you can see, there's a little bit of a line shape here between all the variables. And now we're going to go ahead and run it in a actual analysis. But as you can see, it looks like we may have a positive correlation because higher birth weight is related to higher IQ, it looks like. Well, we're going to run this bivariate here. We're going to do analyze, correlate, bivariate. And we want to do that Pearson and the two-tab like we always do. All right, we're going to do it. There we go. Analyze. I forgot. Correlate, that's right. Analyze, correlate, bivariate. Go to variables. We got our Pearson and our two-tab on. All right, so as you can see, the correlation is fairly significant between IQ and birth weight. And as you can see, birth weight and IQ is obviously the same correlation. So it's 0.91, it's significant at the 0.01 level, which is pretty significant. So as you can see, again from the data, once more, the data is volume here. So our data is a little different, but it was the same in that we had this really high correlation and it was significant. So we'd say that the relation between IQ and birth weight was explored using Pearson's correlation. There's a significant positive correlation. Ours was even higher than that. And this suggests people who had higher IQ scores had higher birth weights. An important thing to remember though, guys, is that correlation does not equal causation. So even though we know that those two variables are related, we haven't been able to conclude anything yet about which one causes which one. It just tells us that the two of them are related to each other. It doesn't tell us why they're related or give us cause and effect. That can either come from your research or from a different statistical analysis called regression. So regression focuses on using the relation between two variables for prediction. Least squares regression line is the prediction line that minimizes the total error of prediction according to the least squares criterion, which I'll talk about more when we do office hours on Wednesday. And essentially, you're coming up with the equation that you do for a line, right? Like y equals mx plus the intercept. And so y is the predicted value of your variable. B will be the slope of your line. X is just the value of X because you're predicting Y from X. And then A is your intercept when X is 0. So I'm going to open up the new data set, and I want you guys to know that I did not write this specific slide, so I'm going to talk very awkwardly about sports. That is not my doing. Let's open data. Jeez Louise, okay, it should be fine, hopefully. Okay, good. It looks like it's all fine. Okay, so what I want to do is we want to know if we can predict the number of runs a team scores. I'll use a real word there, with the number of hits that they get. So our X variable is going to be hits because we were trying to predict how many runs, right? So let's make a scatter plot first to look at the relation between hits and runs. And then we'll input runs on the y-axis, so I'll do that. So again, we'll go to graphs, legacy, scatter dot, simple scatter. On my y-axis, they want to see runs. And x-axis, we'll do hits. Okay. Wow, definitely looks like there's a relationship. So it looks like we may be able to have a regression here. We'll take a look. And then I want to do analyze regression linear, and we'll see what happens. So our dependent variable is, oh, I'm on the wrong data set. Here we go. Analyze regression linear. And our dependent variable, again, guys, is runs. That's what we're trying to predict. And we're trying to predict it from our hits. And let's see. Yeah, but it looks like our model is significant. As you can tell right here in the significance. And our coefficient is significant as well. So we're able to build that equation that we had earlier. Here's the data. So this is how much variance is explained by our hits variable and runs, so that's good. And as you can see, the model is significant. Then we look at our beta, right? So this is our coefficient for when we make that equation, which I'll show you on the next slide. This is the numbers that we need to use. So we have this 0.636, which is our hits, our coefficient, right? So that's our slope essentially is 0.636. And our intercept then is this variable. So that means that with 0 runs, a team gets negative 223 hits, which again is not interpretable just because you can't interpret that 0. Sometimes you can though, because some variables you can have a negative value. This is not one of them. But essentially, this is our equation, right? So we're predicting that runs equals 0.636 times hits minus 223. So let's add this line to our scatter plot and see what happens. So I'm going to double click the chart. I'm going to click this line button on it. And this button, I believe. I may have clicked the wrong button. Hit, undo. I'm going to go ahead and click this guy. We're going to use an equation to get there. So I'm going to make it the equation that we talked about in the slides. 0.636 minus 223.159. So as you can see, that line does look pretty good. It looks like it's not very far off at all. It helps us see that our regression does make sense. That if you predict X hits, you'll be pretty close to the true value of how many runs the team scored, which is the point of regression, so that's good. And it helps us figure out whether or not we have a good predictor line. I'm going to keep it pretty short, guys. That's how you run a regression. That's how you can predict the Y values from the X. I'll talk about this more in person on Wednesday if anyone has any questions. I'm going to look at the activity real quick. So for the activity, we're doing a lot of similar things. A researcher for fictitious companies examining fairness and salaries within the company. She wants to determine whether there's a relation between years of employment within the company and salary. So we're looking at salary, gender, and years. So I'm going to open up the salary data file that I'll put on D2L. This is the last one I'll open tonight. All right, where do we go here? So let's look at the scatter plot to see the ratio between years of employment and salary. So I'll do graphs, legacy, scatter. Simple scatter. And I do years and salary. Let's see if we have a relationship. Definitely looks like we have a bit of a positive relation, which makes sense. The more years you work, the higher your salary is. So I'm going to go back into the activity. And we treated salary as our dependent variable because that's the thing that we're trying to answer the questions about. And so it looks like higher years in the company means a higher salary. So now I'm going to do the actual correlation there. So analyze, correlate, bivariate. And again, we're doing salary and years. And as you can see, we have a significant finding there, which I believe is probably talked about in here. Yep, we have a significant correlation, and it's positive. So yeah, that's positive and very strong correlation. Very strong, the best correlation. So it helps us understand the relation between the two variables, but if we wanted to know how much it changes every year that you work for the company, we would need to do the regression to understand what a 1 unit change in years working for the company does for salary. So I'll do the analyze regression linear, and we'll take a look at it right here before we sign off. Analyze regression linear. The dependent variable again is going to be salary because that's what we're kind of trying to predict from years. And it looks like years is significant. So for every 1 unit change in years, your salary would go up by almost $3,000. And we also can see from our R squared that 68.8% of the variability in, see right here the R squared, 68% of the variability in salary is attributable to differences in years of employment at the company. And then when you look at the regression coefficients right here, like I was showing you on the other page, you can see that the intercept for regression is constant, right? So this is the expected salary for someone who just started the company, right? So that's this number. It's about 31,000 with 0 years of experience. But for every year of experience that you have, you gain an extra, you essentially get a $3,000 raise just about. So you can turn that into an expression just like we've done so far. And then you can follow the same steps to add the line, and it'll just further prove you that you've got a pretty good looking prediction line. And then I will review t-tests on the Wednesday office hours. I will leave this for you guys to take a look at too on your own. And all right, guys, the last thing I want to talk about real quick is the assignment that will be due this coming Saturday. Um, you'll have to enter your own data again, but you're just doing some regression here. Remember to round all your numbers to 2 decimals. First, you'll make a scatter plot. Then you'll run what you need to run to find out if there's a significant correlation. And then after that, we'll do some prediction. And remember, predictions, you use regressions. And then that'll be kind of it, guys. Just make sure you put in your output. So that's kind of all I have for you on that front right now. This will all go up on the D12 site, and that's all the information I have for you. And I look forward to answering your questions. Hopefully we can finish out this semester strong. All right, thanks, guys. Have a good